from Brown University and welcome to our physics class. I'm here at Brown University because my son, Bari, who had orientation at Brown yesterday. We have two students in our class today. Can you introduce yourself?
Yes, my name is Bari. I'm a graduate physics student at Brown University.
My name is Suborno Bari, and I'm doing my bachelor's in NYU in math and physics.
So, when we talk about physics, physics covers everything from atoms to universe itself, right?
Mm-hmm.
In this course, we're gonna learn everything from atom to universe, right? Today we're gonna focus on kinematics, right? Can you write all 6 properties of kinematics?
All right.
Oh, before that, what are the differences between kinematics and dynamics?
Well,
kinematics is about how objects move, and dynamics is about
why objects move.
So kinematics describe the motion, and while dynamics explains the motion, right? Can you, Isaac, write all 6 properties of kinematics?
So essentially what that means is that kinematics is going to tell you how an object is going to move. For example, kinematics might explain what the path of a projectile will be, while dynamics more focuses on what force is required to make an object move. So
Now,
let's talk about the properties of kinematics.
6 properties of kinematics. Can you make a list?
So kinematics and its properties are equations that are dependent on...
No. Can you write them down? All 6 properties.
Oh, you mean the equation?
No, all 6 properties.
Properties.
Like
Yeah.
distance, velocity,
Oh,
and acceleration.
Yes.
So now everything in kinematics depends on 6 properties. Distance.
No, please write it down because these are the students who never seen this before.
Distance. I'm sure you already know what that means. And this is symbolized by the symbol D.
Mm-hmm.
Then we have velocity, which is, of course, how fast something is going.
Mm-hmm.
Then we have acceleration, which is how fast the velocity is changing. When you push on a brake in a car and you slow down, that means you have a negative acceleration because your velocity is decreasing.
Right. What about displacement?
Yup.
Position?
Yup. Please stop. Okay. So then we also have displacement.
Mm-hmm.
We have displacement, speed, which you probably won't see that much, but I'll symbolize it with an S. And finally, time.
Have that?
Yeah.
Lab, can you describe out of these 6 properties, right?
Mm-hmm.
We call them, properties, 6 properties. How many of them are scalar and how many of them are vector? And before you do that, can you tell us what are the differences between vectors and scalars?
Yes. So a vector is, let me write it here. A vector is an object that has a direction and a magnitude and direction. So for example, here is an arrow, and this arrow has a direction pointing this way, and it has a magnitude given by some size. This arrow can represent the velocity, it can represent the acceleration, it can represent displacement. These are all vector quantities.
We've had this in a terrible house.
But
Can you give a size?
For me to help in some
Yeah.
respects?
Can you give a size of this vector?
Can I help
Sure.
you?
So say 5.
Can you double the size now? Draw
Okay.
another vector. This is double the size. So these
This
two
is-
vectors, what is the similar and what are the differences?
So these two vectors are in the same direction, but this one has double the magnitude of this one.
Okay.
Alright, so what really are vectors? Are they just some funny arrows? Well, no. It's about where the wind is flowing. He'll often say it's flowing at 15 miles per hour, like pretty torrential, at 37 degrees to the northeast. What the heck does that mean?
Good analogy.
Well, please stop. Well, the thing is, when we specify the magnitude of the wind speed, we specify how fast is it going. Is it just a little breeze, or is it like a tornado? So, is it going to push you only a little bit, or is it going to push you a lot? And the same thing with the direction. not like the wind is always going to flow north. The wind, you have to specify the direction of the wind sometimes with respect to your own location. So 37 degrees to the northeast, in this case, you probably learned in your geography class that this direction is north and this direction is east. And of course, we can also label the other two. 37 degrees to the northeast thus means we're going 37 degrees up, which you learned
And
in your
also tell them
trigonometry.
when you measure the angle always start from x-axis to counterclockwise.
Yeah. Okay. So now that means that 37 degrees to the northeast, thus means we start from east and we go 37 degrees. You probably learned what that means in your trigonometry class, and that's the direction the wind is blowing. So you can't just say it's at 37 degrees to the northeast. Then how do I know how big the wind is? And you can't just say it's 15 miles per hour. Then how do I know where the wind is going to take me? I have to know both in order to get all of the information that I need about the wind. So there are some things that don't have a direction. As an example, let's take time. You don't say time is going to the northeast or to the southwest. You don't say time is going in a specific direction. All there is to measure is the magnitude, the difference between the time now and the time at some point in the past. All there is to measure is the magnitude because there's no such thing as the direction of time. So that's what a vector is supposed to be. It's supposed to wait, please.
Yeah.
A vector is just supposed to tell us what the magnitude is and what the direction is. So objects that have both magnitude and direction are called vectors, and ones that don't are called scalars. And some scalars are just the magnitude of vectors. What does that mean? Well, as I said earlier, a magnitude is just a number by itself, like 15 miles per hour. And so a scalar is just like a regular number, like, for example, speed. If we're talking about where a car is going, we could say that it's going to towards the north at 30 miles per hour. But then this is specifying the velocity, which has both magnitude and direction. If we want to specify just the speed of the car, then we ignore where it's going and we just talk about the magnitude. So that's scalars and vectors.
Very good. Now, Raf, can you circle the 6 properties? Can you circle the vectors by it? Circle the one that is vectors.
Okay, so velocity is a vector.
Why velocity is vector?
Because it has a magnitude and a direction. And acceleration is also a vector. And displacement is also a vector.
So 3 of them are vectors and 3 of them are scalars.
That's right.
Okay. Can you now take this opportunity to teach us 7 fundamental quantity?
Yes. Okay. So the 7 fundamental quantities are.
Can you list them without erasing this important thing?
Okay. Let's see. Yeah. So
number 1.
One.
Time.
Okay.
It's literally right there.
Okay, time, which 2. Is measured. Okay, let me write quantity. Right. Okay, quantity and units.
And SI unit.
Okay, SI.
What is SI unit? Can you take your time and explain what SI unit means and what is not SI unit?
Yes. So the entire world has agreed on a system of international units that all physical measurements should be taken by. So, for example, whenever you measure time, anyone in the world has to measure time in seconds, not in milliseconds or nanoseconds. Everyone has agreed to measure time in seconds. When you measure length, you have to measure length using meters, not feet or kilograms or inches. This? Okay, so let me show you. Time.
I'll give you a chances of explain it again. So for the students who understand your explanation better, they will be benefited by you, and so on.
Okay, so the SI unit for time is seconds. Okay, the next quantity is length. Okay, the SI unit for length is meters, and the next quantity is mass. The SI unit for mass is kilograms. Okay,
this is physics.
This is physics, not chemistry. And the next SI unit is, let's see, luminosity.
The luminous intensity.
That is
Right?
not how you spell
Luminosity.
luminosity.
Okay, this is not English class.
Yes, it is.
Luminosity.
And anyway, they're never going to see this on the actual test.
Okay. So luminosity is measured in candela. Okay. Next one is
Current.
current. Okay. Current is measured in amps or ampere. Okay. And let's see, there are 7. Let's see, what else am I missing?
Temperature.
Temperature. Okay. Temperature is measured in Kelvin. Okay. So, for example,
And then the final one. Okay, yeah, sure. Go ahead.
so for example, in the United States we use Fahrenheit usually for temperature, but everywhere else in the world we use Celsius. But neither of those are the SI units for temperature. Whenever you make a scientific measurement of temperature, you always have to express it in Kelvin. That is the internationally agreed to system of units for temperature.
Number 7, mole, amount of substance.
Okay, amount.
That's more or less like chemistry, but hey,
right.
these are fundamental quantity in the universe.
And the amount of substance is expressed in moles.
Isaac, now you explain 3 of them and give an example. I would choose 3 of them for you, and you're gonna explain them, and Raf gonna come back and explain 3 of them. You just define them and give an example. Go take 3 of them, 3 of your most favorite one and complicated one.
I don't know what he said at the end of that sentence. I don't think he knows it either, but let's see.
We are not. This is not a presidential debate.
Okay.
You have to wait till 2048.
All right. So we're not gonna pick 3. Actually, we're gonna pick all 7. Okay.
No, you pick 3. Pick
Why?
amount
3,
of substance.
3 is boring.
Sure. All
Okay.
6. All 7.
6. Okay. So first of all, he couldn't even name all 7, let alone explain.
With external assistance.
Okay. Okay. You are ridiculous. So let's start with time. Now, time is probably the hardest one to explain of all of these, but basically, I mean, at one point.
You're gonna explain time. You're gonna explain length. You're gonna explain mass. You're gonna explain luminosity. And
Oh, he's not gonna explain it.
Yeah.
He doesn't even know the name of it.
Okay, go ahead.
Okay. So, at one point, we might have an object in one state, like a full egg, and then in a different point, we might have the same object in a different state, like the egg is now cracked. And it's not like there's anything we can do to put the egg back together perfectly into its original state. It's not like we could just clean the yolk up, put it right inside there, put all the egg shards back in their original place. So there's no way to go from here to there. There's only a way to go from here to there. So that means that this change in state is what we call time. The change, time is all we use to measure the change in the state of an object. So that's essentially what time is. It's like our ruler for change. So now, what about length?
No,
Well,
you did not give me an example. Let's say draw a cut. The distance.
okay,
your
okay,
time.
I got it. Okay. So, I mean, a very simple example of this change is, let's say this car is going at 30 miles per hour constantly, and so.
And put a distance.
Dad,
find the
please.
time.
Yeah, I got it. Anyways, they don't even know any of the equations of kinematics yet. So.
Oh no, we're gonna heading that direction. Yeah.
Okay. So let's say it's going at 30 miles per hour, and so let's say this is at 0 seconds on our stopwatch, and then 5 seconds later, we can see there's a big change in its position. So now, let's say an unknown amount of time has passed, and we can only measure the change, which is, let's say, I don't know, 10 miles. So 10 miles, 30 miles per hour, and we want to see how much time has passed. Well, it's really simple because this is going at constant speed. What is 30 miles per hour actually mean? Well, 30 miles per hour is 30 miles per 60 minutes, right? So then, how long would it take to go 10 miles? Well, it should be pretty common sense that if it goes 30 miles in 60 minutes, as they say, the rate is the amount of stuff you do or the amount of change that has happened, so the distance, divided by the amount of time that has taken place. So the change right now is 10 miles. No, the rate right now is 30 miles per hour. The change is 10 miles. So it should be very trivial to find the time. All you have to do is multiply both sides by t, and then divide both sides by 30, which gives you 20 minutes to travel 10 miles. So that's an example of time.
And 20 minutes is not as a unit, and can you convert it to as a unit?
All right. So now, what you may notice is that this doesn't use our SI units for either time or length. So let's change that. Kilometers per hour, kph. But since we're more familiar with miles, we're just going to have to convert it. Miles are actually a lot bigger than kilometers. And a kilometer is 1,000 meters, which means realistically a meter would be so small to scale that I couldn't even draw it on the whiteboard. So, what is the conversion between 1 mile and 1 meter? Well, an easier thing to keep in your head is the conversion between 1 mile and 1 kilometer because of how similar they are. And then it's very easy to convert from 1 kilometer just to 1 meter. So, what is this? Well, 1 mile is actually just 1.609 kilometers. So what you're going to learn to do is, since 1 mile is equal to 1.609 kilometers, that means realistically, if we have 1 mile divided by 1.609 kilometers, this would just basically be equal to 1. So that means we can multiply anything by it and still get the same thing. So for example, we can multiply this by 2 kilometers, and whatever we'd get out the other end would still be 2 kilometers, just converted to miles. So, in this case, of course, we have 10 miles. So we're going to convert that to kilometers. So, what we would actually have to do is reverse it. But of course, dividing 1 by itself just gives 1 back. So, we got 1.609 kilometers divided by 1 mile, and this conversion will still work because both the top and the bottom are equal. So, we have 10 miles, and all we have to do is cancel this out, and we get that the distance traveled is actually 16.09 kilometers. And from there, if we really want to, we can convert this in itself to meters to get 16,090 meters. But usually, just keeping it with kilometers and switching the final answer to meters gives us easier numbers to work with. So, let's convert this to 16.09. And in a similar way, we're going to have to convert 30 miles per hour. Sorry, kilometers. In a similar way, we're going to have to convert this speed number. So, this is a little more complicated because it's 30 miles per 1 hour. And now we need to multiply that by our mile to kilometer conversion factor, which looks like this. And then we need to multiply it again because this is just going to give us kph. But we want kilometers per second to give us that perfect SI unit. Huh? Yes, I know, but kilometers gives us easier numbers to work with. Alright, so then 1 hour is, of course, 3,600 seconds. So now, all we have to do is multiply it out. 30 by 1.609 gives us exactly 48.27 kilometers. And then we divide that by 3,600 seconds. an easier thing to do to help keep it in your head might actually just be to see how many times this goes into this. This just gives us 1.609 divided by 120 kilometers per second. And so now this is just going to be equal to, I'm going to need a calculator for this. This is just going to be equal to 1.609 divided by 120 is just 0.0134 kilometers per second. And you might think, hey, that seems pretty slow. But since this is kilometers per second, when it comes to meters per second, it's actually huge at a whopping 13.4 meters per second. All right, great. So now we've converted this to a valid unit as well. All right, so now we can find the time more comfortably. This is just going to be velocity, or our rate, is equal to our distance divided by our time. So we just get that the velocity is 13.41. The distance is 16.09 kilometers, but let's be careful here because this has to actually be converted to meters since we're using meters here. This is 16,090, and we divide that by the time. So that means that we multiply both sides by the time, and we divide by 13.41 to get 1,200 seconds. 1199.8, but that
1200 seconds is equal to 20 minutes.
Yep, exactly. So that means we've explained both time and length. In math, you probably already understand from basic definitions. Luminosity is just how bright an object is, how many light rays or how much light energy it can let out. Actually going to be saved for later. Now, temperature is very easy. You probably already remember temperature as being measured in Fahrenheit. But the thing is, most of the rest of the world, as you probably heard, uses Celsius. So I believe this converts to about 25 degrees Celsius, but I don't exactly remember.
No, all you need to do right equation.
Right.
Is equal to.
So the Celsius is going to be equal to 5 over 9. 5 over 9 times the Fahrenheit number minus 32. So
Fahrenheit is equal to. No, you don't have to do anything.
No. So for example, 73 Fahrenheit minus 32 gives us 41. Multiply by 5, divide by 9 gives us 23 degrees Celsius. So I was almost there. All right. So
the Fahrenheit equation?
Yeah, it's just the reverse. So of course this is just going to be the inverse formula, which looks like this. So now
finally write the Kelvin equation.
Okay. So now Kelvin is just an offset version of Celsius. Now, why do we need an offset version of something that already exists? Well, that's because Kelvin has been specifically outfitted so that 0 Kelvin means that the temperature is absolute zero. All of the particles in an object have completely stopped moving, which, by the way, if you don't know already, temperature just means the energy, the moving energy of all the particles in an object. So, if there's 0 Kelvin, all the particles have completely stopped moving. This is why we need Kelvin. And, of course, Kelvin is just an offset of Celsius by exactly 273.15 degrees. So, substance is essentially just a way of measuring how much of something there is. So, the thing is, 1 mole of something is exactly 6.22 times 10 to the 23 atoms of that thing. So, for example, 1 mole of carbon is 6.22 times 10 to the 23 atoms. And this may not seem like much, but written out fully, it would look like this. So yeah, Avogadro's number is pretty big. He's trying to count the number of zeros. I'm just letting you...
That's only 21 zeros.
Yeah, because... So you're telling me you failed basic scientific notation.
Okay.
Sad.
So speaking of scientific notation, quickly give the student the equation for scientific notation.
Alright, so scientific notation is essentially, if you have any number, like, for example, 7, 8, 5, 0...
The formula. 8 times 10 raised
No,
to
Dad, that's a format, not a
the
format.
format. Right?
Alright, so if you have a number like 78,500, what we do with scientific notation is, first, you already know about exponents, so the powers of 10 are 10 to the 1 is just 10, 10 to the 2 is 100 with 2 zeros, 1,000, and so on and so forth. So here's what we want to do.
Format, right? The format.
Essentially, we kind of split off the first digit, and there were 4 digits here, right? That means this is of the order of magnitude 10 to the 4. Of course, 10 to the 4 is equal to 10,000. So hopefully you can see where we're going here, because now, of course, if we just multiply this by 7.85, we get 78,500, our original number. So the format is, we want this first digit, along with anything in the back. Essentially, we want a number less than 10 multiplied by a power of 10. So in this case, 7.85 times 10 to the 4, but in general, a times 10 to the b.
And right, a is always less than?
Yeah. Now, why is a always less than 10? Well, if a was equal to 10, then all we would have to do is write 1 times 10 to the b plus 1. We could just add to the power of the scientific notation. And same thing goes for if a is greater than or equal to 10, we could just write a divided by 10, which would now be less, times 10 to the b plus 1. So yeah.
Now explain why b has to be a whole number.
I mean, 10 to the n, if n wasn't an integer, it could be anything. But 10 to the 6.2837 doesn't really tell you much about a number. You can't really write this out off the top of your head. But if you see 10 to the 6 times 5.73, you can very easily write this, because this is just 5 followed by 7.3 and 4 more zeros.
The first day of the class, I wanted to cover 2 more concepts. And while covering
Why doesn't